Now we're going to move on to the economy of sedimentary rocks. So, sedimentary rocks is a group of rocks that is also economically important, just like igneous rocks, as we saw in Chapter 4. Sedimentary rocks are useful for energy and also for mineral resources. These rocks are usually mined for non-metallic mineral resources. In this case, obviously, the word mineral is a very broad term, and it's different from the geologist's strict definition of a mineral. These type of resources are extracted and processed for non-metallic elements that they contain, or for the physical and chemical properties that they possess, such as those on table 7.1 of your book, which is also this figure right here. Per capita, the consumption of non-fuel resources in the US is nearly 100 metric tons, of which 94% are non-metallic minerals, which themselves are divided into building materials and industrial materials. Some substances fall into both building and industrial materials. For example, limestone falls into both categories. As a building stone, it is used to make cement and is crushed rock itself to make dew. And as an industrial material, it is used for the manufacturing of steel and also in agriculture uses, because it will not neutralize the acidic soils. I would recommend that you read the other uses of the different non-metallic minerals and other sedimentary rocks. Other sedimentary rocks themselves, however, are useful as well. Quartz arenite, which is basically quartz sandstones, are used for glass making, for example. A claystone is the source for bricks and ceramic. And the unconsolidated sand and gravel is used for road mix and construction fill as well. So the tremendous industrialization that the Earth has seen in the past 2 centuries has been fueled, and it is still being fueled by the burning of coal, petroleum, and natural gas, as some of you know. About 81% of US consumed energy still comes from these sources. The image above shows the sources of our energy and the major users of that energy nationally. It also shows the percentage given to each user of the energy type, and the percentage as total energy received per each user from each energy type. I know that was a little confusing, but the graph itself explains it quite well, I think. As you can see, our reliance on the fossil fuels is still very clear, and the projection from the Department of Energy is that our use of fossil fuels will continue to be very significant in the decades to come, despite our use of some of the renewable resources as well, such as solar, hydroelectric, wind, and geothermal as well, and some energy sources like nuclear electric power. So we still rely quite heavily and will do so on fossil fuels in the future. In addition to oil and natural gas, coal is commonly called a fossil fuel. This is termed that way because when coal is burned, the energy that was stored by the plants from the sun exposure that they received millions of years ago ultimately make up the coal, and it will be or the plants themselves ultimately make up the coal, and that energy that was stored from the sun will now be released with the burning of the coal. So it is a literal burning of fossils, which are ancient fuels. In the US, coal fields are widespread, as you see from the map, and contain supplies that should last for hundreds of years. Coal is quite plentiful, but its recovery and use present a number of challenges. Surface mining, for example, can turn the countryside into a scarred wasteland, as you're seeing in the top right image. And if careful and costly reclamation is not carried out to restore that land, then it can result in such awful images. Today, all of the US surface mines are required to reclaim the land. Underground mining is perhaps not as harmful to the landscape, but it has costed many lives and a lot of health problems to the workers, as well as the people who are affected by the burning of the fuels. Nowadays, the mining of coal is quite safe due to the regulations in the US at least, but there are still hazards such as collapsing roofs and gas explosions, for example, in the underground mining. Also, the burning of coal produces emissions that affect the environment and human health. Principal emissions resulting from coal combustion include some of the following things. So they include sulfur dioxide, which overall contributes to acid rain, as we saw in chapter 6, and it gives respiratory problems. It contains nitrogen oxides, which contribute to smog and respiratory problems. It causes particulate matter, which contribute to smog, to the haze, and they cause lung disease and respiratory problems as well. And also CO2, which is the primary greenhouse gas, which plays an important role in the heating up of our atmosphere, as we will see in chapter 20. About 60% of the US electricity comes from oil and natural gas together, which also have an effect on our atmospheric print. The improvement of recovery techniques have made natural gas and petroleum use actually surpass coal use, which was not the case in the past. Petroleum and natural gas are also derived from the remains of organisms. However, oil and gas come from microscopic organisms like plankton that are buried were buried millions of years ago, rather than from organic matter that was buried in swamp-like areas. So we'll go through the process in a bit. The organic matter which oil and natural gas originate from is from sedimentary bases intermixed with mud, sands, as well as other materials. So these materials protected the material from oxidation and from other chemical reactions. As they were buried, the increasing pressure and temperature that was caused made the chemical reactions further transform this material into fluid and gaseous hydrocarbons, which were called now petroleum and gas. The petroleum and the gas are typically mobile, unlike the organic matter from which they form, because these are fluids now. So these fluids are squeezed by compaction out of the rock where they formed, typically being a mud or a shell. So this particular rock where they formed is called the source rock. They then flow towards more permeable rocks, like sandstones. So permeable are rocks where there's a lot of pores that are interconnected. So in this case, the pores in between the grains are larger, in sandstones I should say, and this type of rock where they stay is termed the reservoir rock. Okay, so where they're produced, source rock, where they typically flow into, reservoir rock. When these pores contain water, the other fluid typically migrates above them. So the oil or the gas typically migrates above the water as it is less dense than the water. And so they try to escape upwards. Sometimes they do meet their goal, so they're able to escape, but sometimes they stay trapped by some sort of geologic environment that impedes their further movement. This type of environment is called a trap. So you have source rock, reservoir rock, trap. And typically this trap is also accompanied by an impermeable formation that is above, which is termed the seal. And so a seal can usually be a shell layer, and as we saw, shell doesn't allow fluids to flow very well through it due to the alienation of the grains. But it can also be things like a salt dome that doesn't also have any pore space because the crystals grew to cover any possible space. So the image in the slide shows a few different scenarios in which this whole process can occur. Again, before we go through the different scenarios, the 5 different aspects of oil recovery, the 5 different things you need for it, oil and gas recovery, are migration and time, so migration of that matter and time for it to get buried. You need a source rock where the organic matter actually comes from. You need a reservoir rock, which is going to be where the fluids, once they're made into fluids, escape to. You need a trap mechanism and a seal, which prevents these fluids from escaping further. And there you have it. Then you can recover it. So let's go through these scenarios where you can get entrapment of these fluids. So in the first case, A, we have an anticline. An anticline is a geologic structure where the beds or the strata form an A-like shape. So A as in the letter A, like shape, when looking at it in a cross-sectional view. So this view type is called cross-sectional view, and you're seeing that these strata kind of make an A feature. Here you see that the cap rock or seal, right here, is accompanied by the anticline itself as forming the trap. So they're working together, the seal rock, and then the trap is the structure itself. So they hold the gas and oil stable in that location without anywhere to escape due to the lack of the permeability from the cap rock. And the need for the fluids to rise upwards from the fluids don't let them go to the sides of that anticline trap. Case B shows a fault trap. So in this case, the layers are a bit inclined. As you're seeing them, they're a little bit inclined, not quite horizontal, which provides a slight angle for those fluids to migrate upwards through the reservoir rock. Here, they will travel upwards until they meet the fault, at which point a cap rock now lies above and to the side of the fluid. So as you're seeing from this fault, this layer used to be up here, so the fluids would have been able to continue on their way upwards, but because of the fault mechanism, this layer now lies a lot lower, hence making the seal for the fluids not to flow upwards. Case C right here shows a salt dome trap, similar to the anticline in a way, but with a slight difference in the outcome of the flow. So I think you're starting to get the idea by now of how it works. So I'm not going to go ahead and explain it, but you can see that basically there is a seal mechanism from the layer above and from the sides due to that salt dome. In the last case, case D, it shows a stratigraphic trap. So in this case, the surrounding rock is all impermeable, so there's no possibility for further upwards migration from any of the small pinch outs where that oil and gas are locked up. So whatever the type of trap system that you have, when the drilling itself punctures the lid created by the seal or the cap rock, the fluids, which are under pressure, will migrate from the reservoir rock pores upward through the pipe. It is very rare that the fluids will actually rise all the way up to the surface without the need for a pump, but it has happened in the past. And so that's how we get the fluids out of there, through that puncturing of the cap rock for the most part.